Welcome to the presentation of easy strategies in complicated games, where easy strategies means that a computer can implement it, and complicated games means that no generic algorithm can ever give an epsilon approximation of the value of this game. More precisely, we will talk about finite memory strategies in partially observable Markov decision processes with long-run average objectives. During this presentation, I will mainly show examples and motivate the problem. In a finite partial observable Markov decision process, from now on simply POMDP, there are finitely many states, actions, and signals. The game is played in stages. At each stage M, the decision maker chooses an action. This action, together with the current state of the game, determines a stage reward, GM, and the distribution over the next state. The state dynamic is imperfectly observed by the decision maker, who only receives a stage signal before continue playing. Let me contrast POMDPs with other related models. POMDPs is a generalization of hidden Markov chains because it includes a decision maker. In this sense, it can be seen as a controlled hidden Markov chain. It obviously generalizes Markov decision processes because it considers a hidden component. POMDPs can also be described as optimal control problems. Let's see a very simple example. In this example, there are two states, state up and state down, two actions, action up and action down, and two signals, signal change and signal wait. All transitions are possible regardless of the action played. Signals are such that the decision maker is notified when the state changes from one state to the other, but nothing more. Stage rewards are given as follows. Playing action up yields a reward of 1 only if the state is state up, and action down yields a reward of 1 only if the state is state down. If the decision maker knows the initial state, then she can obtain a reward of 1 in every stage by playing the correct action. On the other hand, consider the initial state is random, and the decision maker only knows its distribution. For example, consider the distribution with a quarter probability for state up and 3/4 probability for the state down. Then, playing any strategy yields a sequence of random rewards. To aggregate this sequence of random rewards, we use a long-run average objective. In many of the applications of POMDPs, the duration of the game is huge. Thus, considerable attention has been devoted to the study of POMDPs with infinite duration. A standard long-run objective is the expectation of the inferior limit average reward, which is given by the following formula, where GM is the stage reward, this is the lim_inf of the average reward, and then the expectation, which is defined by an initial distribution P1 and a strategy sigma. The value is the supremum over all possible strategies. This value has been extensively studied, and it coincides with other classical definitions, including asymptotic value, uniform value, general uniform, long-run average, uncertain duration process value. All those prove this series of equalities. Thus, strong results are available concerning the existence and characterization of the value V infinity. This is in sharp contrast with the study of long-run epsilon optimal strategies. Indeed, before our work, little was known about sufficiently complex strategies. Available results include stationary strategies are enough for MDPs, where the state dynamic is perfectly observed. Belief stationary strategies are enough for blind MDPs or POM MDPs with an ergodic structure. Note that belief stationary strategies cannot be encoded in a computer since they depend on the current belief obtained at each stage using bias rules, and there are infinitely many possible beliefs. So, what families of strategies are able to approximate the value of general POMDPs? We show that finite memory strategies suffices, and that has some important consequences. Before going to the details of our results, let me remark that in POMDPs, the decision maker has to balance short and long-term rewards and includes the possibility of irreversible actions, which naturally exist in applications. These properties make POMDPs an interesting model. About computational complexity. Giving epsilon approximations of the value of a POMDP is a complicated problem. So complicated that there cannot be any generic algorithm that approximates the value of a given POMDP. This class of problems is called undecidable and includes the classical halting problem for Turing machines. Therefore, the best we will ever be able to do is to give either lower bounds or upper bounds that approximate the value of a POMDP. With our result, we can give lower bounds, which also proves that it is impossible to give upper bounds approximating the value of a POMDP. About the value function b infinity, we deduce that it is lower semi-continuous with respect to the transition function. This is based on a previous result of continuity for Markov chains with respect to the transition function. Before ending this talk, let me show another example. In this example, the initial state is fixed and known to the decision maker. From there, with equal probability, the state moves to either of two subgames, and the decision maker is informed of this movement through the initial signal. If the state moves to the first subgame, the optimal strategy is playing action A forever. Moreover, playing action B once leads to an irreversible move of the state, and the reward will be 0 forever. If the state moves to the second subgame, the optimal strategy is to play action A until getting signal S2, play action B once, and restart the cycle. Again, deviating from this optimal strategy results in an irreversible movement of the state, and the reward will be 0 forever. Let me argue that we need to remember the initial signal to play epsilon optimally in this POMDP. After the first signal, in each of the subgames, we can get an arbitrarily long sequence of actions and signals A as 1, A as 1. Then, upon receiving signal S2, an incorrect action will make us obtain a final reward of 0. The only way to know the correct action is to remember the initial signal. Therefore, since the value of this POMDP is 1, we need to remember the initial signal to approximate this value. In blind MDPs, where there is only one signal, recalling only the most recent history, meaning actions and signals, is enough to play epsilon optimally. But this is not true for general POMDPs, as we just saw. In our paper, there are more examples illustrating the challenges of POMDPs and how our techniques solve all of them. Some open questions are proving or disproving the continuity of the value function b infinity with respect to perturbations in the transition function. Also, investigating other classes of strategies like belief partition. Thank you very much for listening to my talk.